Morning, students. We're going to start magnetic fields today. Oh. When this tablet catches up, something's wrong with the tablet. Hang on. It's better. Magnetic fields. New topic. Topic 7 of 16, which means that shortly we will have a test after charges in magnetic fields is the next topic. At the end of charges in magnetic fields, which shouldn't be too long, we will have a topic test, and then shortly after that, of course, you have an exam on the entire first half of the course, or eight topics. Okay, so where do magnetic fields come from? Imagine this is a situation where we have a charged particle. You might think of it as a positive proton. Of course, that positive proton has an electric field associated that might look like this. Directed radially out, meeting the charged particle, the sphere that is the charged particle. We imagine it as a sphere anyway, at right angles to that surface. And we know that all charged particles have this. Anything charged has an electric field associated with it. What about the situation if this charged particle has motion? Relative to something, to some observer. Now, it's been noticed that, in fact, if the observer's moving with the same velocity, there is no magnetic field, interestingly enough. But if the observer isn't moving, then the observer sees a magnetic field associated with that charged particle. And we're going to look at, in this topic, as if it's kind of a bunch of charged particles moving in a line. We call this thing current. This might be the flow of positive charge. Flow of positive charge. This is also called the conventional current. I hope you all learnt that last year. No? I haven't heard this idea. Did I? Yes, I will. So this is a flow of charge with some speed v. Flow of positive charge is a conventional current. Let's have a look at, just so that we understand conventional current. If I have a copper wire and I have electricity moving through it, okay, we call this current I. You know that. What's going on inside? What could we say about the particles inside the charges inside that copper wire? Moving with the current. Okay, so the charges are moving with the current, and we think of, in copper being a conductor, that there's all these electrons, and of course there's many more than this, and those electrons are kind of free to move in that copper wire. How are they moving? Yeah, there's a potential difference across, yeah, and that basically pushes them through, doesn't it? Okay, and we'll say, yeah. That's alternating current. AC goes backwards and forwards. DC goes in one direction. Let's think of this current as DC. And I'll just take away the potential difference there for now. We know that these are little negative charges moving through there and that they do in fact move. How fast do they move? They move really slowly. if I, they might move, they might move at a speed of about a meter every minute or so. They move pretty slowly, actually. Each individual charge itself. But the signal doesn't it? Imagine how our computers how our computers would work if the electrons moved at that speed. Things would take ages. Okay, so but it doesn't. Imagine I take at this end of the wire, and the wire is filled with water. This is the actually this is the way to think about it. This is a pipe, and the pipe is filled with water. Actually, I should have done this first. So it's filled with water flowing through. Okay, it's full of water. Okay, and I take some more water and I push it in this end. What happens at the other end? Whoops. If I place that extra water into that pipe, water, pipe, what happens here? The same amount of water pops out the other end almost instantaneously, doesn't it? Okay. But the water that I pushed in is still here. Okay. The signal that that water is pushed through that pipe has moved instantaneously almost at light speed, or they're very close to, but the water itself hasn't moved that much. And that's how we like to view the idea of these electrons. If I push a bunch of electrons in at this end, then a bunch of electrons are going to pop out at the other end very quickly. Push a bunch of electrons in here by sending a signal through that wire, then the same amount of electrons move out the other end almost instantaneously. In our realm, we think of it as instantaneously. But the electrons that I just pushed in are just at this end still. They're moving very slowly. But the signal moves very fast, okay? Back to, that's what you meant? That's what you meant, okay. So back to conventional current. I've got blue still. Conventional current is the flow of positive charge. That's a pipe. Okay. Conventional current is the flow of positive charge. Okay. So if I said the current is going in that direction, in which direction are the electrons traveling? Yeah, the electrons are traveling opposite. Okay. So electrons are going this way. Okay. I do need you to know that. That will be important later. Back to our flow of these charges. We have some flow of positive charge. I could have just as easily said negative charge. Just say we have a flow of charges moving in this direction. They each have an electric field associated with them. And when we see them relative to some observer moving, then they have a magnetic field associated with them also. With a moving charge, a magnetic field is present in addition to the electric field. Let's go to some more copper wire. Here's a piece of copper wire directed vertically up. I'm going to say that the current is traveling in that direction. When I say current, I mean conventional current is traveling in that direction. How does the magnetic field look? Does anybody know? The right-hand rule is how we tell the direction of the magnetic field, yes. What's the orientation and how would I draw it near this wire? Circling that wire, yes. Okay, so let me just see right-hand rule. So it's actually doing this around that wire. And by the right-hand rule, I'll explain that in a second, I can see that actually, oh, yeah, it's actually going, I've drawn it in the wrong orientation, but that's okay. I'll just put the arrows in the right orientation in this direction, counterclockwise, okay? So this magnetic field, its insignia is B, it is a vector, and it's rotating counterclockwise. I know it actually I've just drawn one. I've only drawn a two-dimensional idea of this magnetic field. Of course, you know that as we move up this wire, then there's more magnetic fields rotating around the wire. Okay, so even though I draw two-dimensionally, always think three-dimensionally. It has the units Tesla. Who's heard of a Tesla coil? Yes, good. What does a Tesla coil do? You've heard of a Tesla coil, but you're not sure exactly what it does. It makes sparks, yes, okay. Because I showed the other class, I'll show you guys. Oh. So there's this magnetic field around this wire. Uh, it has units Tesla, and named after Nikola Tesla, of course. He fell in love with a pigeon, yeah, apparently so. Apparently so. I don't know the whole story to that. I find it hard to believe that he, well, do you love your pet dog? Maybe that's the same sort of thing. I'm not sure. The right hand rule. Who knows the right hand rule? Who has heard of the right hand rule? Oh, just because I said it? Yes, good. Right, that's fine. Allows us to find the direction of the magnetic field. So, oh, comma, knowing of the current, knowing the direction of the current. So when I say current, remember that I'm talking about conventional current. Uh, I have a picture. Yeah, I'll get the picture that I used the other day. That's quite good. You can use the left-hand rule if you want to. You just have to remember to reverse it every time. Yes. Uh, yeah, so I'm going to say that it's possible, but don't do it. Just on magnetic fields, like we looked at electric fields, if I have a magnetic field which curves like that, the direction of the magnetic field at any point is at a tangent at that point to the field. Okay. If I want to draw some magnetic field lines, I can draw them close to each other, or I can draw them further apart. Given the same area, or similar area, uh, this magnetic field is going to be stronger, okay? Has a larger magnitude than this magnetic field, pictorially. Field lines cannot cross. This is not allowed. Okay. And one more thing. If I have a field and I want to know the direction of the field, I have to do this. I have to put a magnet magnet. Red is usually north, I think, is the convention. I usually paint red. Red is the north side. So north, south. We'll talk about why we have a north and a south end later. It's just for convention. So So um, the best way to picture this is that where is north going to face? Well, north is going to uh, north is going to be directed in the same direction as the field externally anyway. So north faces that way, the field faces that way, so to speak. Okay, I'll show that a little bit better in a diagram here. Let's draw another magnet. A little bit bigger. And let's draw field lines around it. Does anybody know what the field looks like around a magnet? Yeah, yeah, it's kind of curvy, isn't it? Something like this. Something like, and that goes off, of course, and makes another curve. This goes off and makes another curve. I'm not going to draw the whole thing. It'll just make a mess. If I know the north side, north end of the magnet, and the south end of the magnet, I I always think of it this way, and that is that the current, the magnetic field inside the magnet has direction from south to north. Therefore, outside the magnet, it must have north to south if it continues on, as if it were going, it rotating through the magnet, okay? As if it were rotating through the magnet. Yes, with the arrows will give you an extra point. If you get that question, which would be nice, getting questions like that, they're good. You get points for the orientation of the magnetic field. You get points for you get a point for drawing the magnetic field approximately correctly, and you also get a point for showing the direction of the magnetic field in the right direction, of course. Okay, there's another image in your text which is pretty good actually. I'll just bring it up here. Sorry. I'll bring that back in a second. Magnetic fields. There it is there. That's perhaps a better drawing than I made before. Okay, so thumb in the direction of the current. This is the right hand rule. Thumb in the direction of the current, and your fingers wrapping around that wire show the direction of the magnetic field. Okay. Put this down here. And just make sure I label it. Okay. Any questions so far? That's easy. So now some concepts that I can't draw very well. So we'll just cut the page, cut the cut the pictures out of our text. Here is a current loop. And so you might say, oh, well, in what situation do we see current loop? Probably there is situations, but I can't think of any that are obvious right now. But just know this idea that if we have a loop moving, a current moving in just a loop, and you say, well, hang on, that will just burn itself out very quickly. Well, there might be a light globe in that loop, in that circuit there, and a battery powering the current. So we have some resistance, and it just powers that light bulb. What does the magnetic field look like? Well, it looks like this. Make sure I've got the orientation right and I'll draw it correctly. So there, down, around. Yep. Okay. So it's kind of goes around in this direction. Is that right? Yeah. Oh. Current in that direction. Okay, I'm pointing my thumb in the direction of the current. The magnetic field wraps around that way. Okay, that way. So I've drawn that circle not very well. I'll draw that circle better. If like so. Have I got that right, people? No? Yes. Goes around behind. Yes. Okay. So that continues to do that all the way around the wire. Yeah, so we'll have a look at the current on the other side. If we go to the other side of the current loop and we point our thumb in the direction of the current, then it comes from the outside in and through, from the back through, okay? So from the back and through. I know this is a little bit hard to picture, okay? Here's another picture. And this is what it looks like if I were to draw all of the field lines around that current loop. I'm not going to try and draw that. You can imagine three-dimensionally, these magnetic fields due to this current loop happen all the way around here, constantly, all the way around. It turns out that through the loop we get this nice current flow, or flux, they call it. Flux is another word for flow, really. Excuse me. So if I were to continue to draw the field lines, that's what they would look like. Who's seen a solenoid before? Who knows what a solenoid is? You should. God, I should have learned this last year. Let's get a picture of a solenoid. Where do I see solenoids? Yeah, where do I see solenoids often? Yeah, it is. Where's a good idea? Good picture of a solenoid. I don't like any of this stuff, really. It doesn't really help us. Oh, these guys. Yeah, here. Okay, these are solenoids. Here is a bunch of solenoids. Now, essentially what it is, through here, through the center of this thing, is, yeah, a lump of metal, essentially, or a metal pipe, solid metal pipe. And wrapped around, you might have seen Actually, I've probably got one. Hang on. I'll see if I can get one to show you. Let me just give me a second.